in the United States, let's say that foreign manufacturers have been tracking their gas mileage for all cars that were imported into the United States. So we know the average for all foreign cars, mu, for all foreign cars is 27 miles per gallon. We want to test whether the mean gas mileage for American cars is the same as the or different than the mean gas mileage for foreign cars. So from that statement I just made, is that a one-sided test or a two-sided test? Okay, Jennifer says two-sided. Anybody else have an opinion? Yeah, take a look, read this. You obtain a random sample of 25 American cars and find that the mean gas mileage for the sample is 23.5 miles per gallon with a standard deviation of 7.82. Same problem we were working with before, except this time what we're going to do is we want to see, well, we know that the average for all foreign cars is 27 miles per gallon. That's the entire population of all foreign cars. They've actually, maybe foreign manufacturers actually track their gas mileage in the United States. For some reason, we know that population mean. So we are taking a sample and comparing it to a value. That's called a single sample t-test, because one of the numbers is a value, a known value. The other number is an average for a sample. In this case, the value for American cars, the mean for American cars is 23.5, is the mean of a sample and its standard deviation, and we're comparing it to a known number for all foreign cars, which is 27. Single samples, one sample, we're comparing it to a certain number. Everybody okay with that? Okay. Yeah, I said different, so it's a two-sided test, and I didn't say greater and not greater. So first thing I'm going to do whenever I do a hypothesis test is I'm going to do I'm going to describe my null and alternative hypothesis. I'm going to click in here and say my null hypothesis is that the mean for American cars is equal to the mean for foreign cars. Okay, if you want, you could even say, oh, is equal to, what were they? They were 27 miles per gallon. Okay, or you could say the mean for American cars equal to 27. Right, either any of these three would be, any of these two, either of these two would be okay. The alternative hypothesis is that the mean for American cars does not equal the mean for foreign cars. You could also say mean for American cars does not equal 27. Either one of these two is okay. That's my hypothesis. Now I'm going to test that hypothesis. Okay, so now, in order to test that hypothesis, I need to see how far apart the mean X bar is from the mean for the foreign cars. X bar for American cars, how far apart is it from the mean for foreign cars? How many standard deviations apart is it? Okay, well, usually I measure standard deviations in terms of the z-score. Okay, well, what was the sample size that I used here? The sample size was 25. So I can't use the z-score because the sample size is too small. Let me write that down here. Okay, if sample size were over 25, I could use the z-score. So I have to measure how many standard deviations apart these two are. In other words, how many z's or how many t's apart. In our case, we're going to look at t's for now. Okay, so the way I measure how many t-scores, how many z-scores, either way, z is equal to x bar minus the mean I'm comparing it to for foreign cars, in this case, over the standard error. That's the number of z-scores, or the number of standard deviations apart that the mean that we got from our sample is from the population mean that we're comparing it to. If we're talking about a small sample size, we're going to say t is equal to x bar minus mu for the foreign cars over the standard error. Okay, in this case, we're working with t. Okay, so I want to prove that these numbers are far enough apart that I have less than 5% chance. Alpha is equal to 0.05. We want our probability of being wrong to be less than alpha. We want it to be less than alpha, less than 0.05. So now, what we're going to do now is we're going to go to the t-table, and we're going to look up the critical value of t in order for us to say with 95% certainty of less than 5% chance of being wrong that that we can reject the null hypothesis. So let me ask you first, if we were using the z-score, what's z-score? What's the critical value of z that we would need to reject the null hypothesis? How far apart do we have to be in these two means in terms of z-scores in order to say that we can reject the null hypothesis? In other words, get less than 2.5% in either tail. 1.96, exactly right. Exactly right. It's 1.96, right? Because that's the z-score that would give us a 2.5% tail on one side, 2.5% tail on the other side. So that's how far away we're past that point if we get a z-score bigger than that. Well, what t-score do we need to do the same thing? Well, that depends on the sample size or degrees of freedom. So let's get our t-table back up again. Okay, here comes our t-table. Here we go, use this one. Okay, so what is our t-table for a sample size of 24 degrees? It's 2.064. 2.064 is equal to 2.064. Had this been a bigger sample size, we could have used Z critical, and that would have been 1.96. These have to be, the mean and standard deviation have to be further apart because of the small sample size than it would have been if we could have used the z-score, right? So this is, the t-test forces us to be more rigorous. So let's calculate to see if we are indeed that or further apart. So what is c equal to? It's equal to x bar, which is 23.5, I think, minus 27 over the standard error. Now, standard error was equal to, what was the standard deviation was 7.82, 7.82 over the square root of the sample size, which is 25 or 5, okay, is equal to, and I'll do the calculation here, which we just did before, as a matter of fact. Is that it? No, that's not it. Okay, I'll clear both of these. We did the proportion since the last time. Okay, so it's 7.82, whoops, 7.82 divided by 5. So our standard error is 1.56. Okay, so let's see. T is equal to, it's equal to 23.5 minus 27 over 1.56. Okay, so let's put that in here. Clear. Let's clear everything out. 23.5, and it can be positive or negative, it doesn't matter, minus 27 equals minus 3.5 divided by 1.56. And so that's minus 2.24. Okay? Is our t-score big enough? Are these two values, x bar and mu, are they far enough for us to reject our null hypothesis? Opinions? Yes, I agree, right? Because t came out to be bigger than our critical value for t, bigger than the size of t that we need for that sample size to say that there's less than 5% chance that we're wrong if we reject the null hypothesis. So we reject the null hypothesis and we accept the alternative hypothesis that American cars, the gas mileage of American cars is different than the gas mileage on foreign cars. Okay, now we could have considered a one-sided hypothesis. Let's say that we believe that American cars use more gas than foreign cars, right? Well, if they use more gas than foreign, if we really suspect that or we have a reason to believe that, okay, let me see, new page. I'll work with this. That's good enough. Okay, let's say that we have reason to believe that American cars use more gas, right? I want that now. What I'm looking to prove is that American cars have lower mileage than foreign cars. So now my null hypothesis, right, is not going to be the mu for American cars. Mu for American cars is equal to mu for French cars, for foreign cars, right? It's going to be that mu for American cars is equal to or less than foreign cars. And my alternative hypothesis is going to be that mu for American cars is greater than mu for foreign cars. Let me think about this for a second. I want to prove that American cars. I got it wrong way. Hang on a second here. My alternative hypothesis is mu for American cars is they get less gas mileage than foreign cars. Okay, and my null hypothesis is that mu for American cars is greater than or equal to mu for foreign cars. Let's think about this. What I want to prove is that American cars get worse gas mileage. So I start with the opposite, so that the alternative, so that I can use my statistic to reject this alternative that they get either the same or greater gas mileage than foreign cars. So my null hypothesis is that American cars get better or equal gas mileage to foreign cars. My alternative hypothesis is that American cars get less gas mileage than foreign cars, right? So now I want to prove that this is true. I need to reject my null hypothesis, accept my alternative hypothesis. Notice that there's always an equality in the null hypothesis. In other words, we want this, if it turns out that they're equal, we don't want to reject the null hypothesis because the point was to prove that they got lower gas mileage, not equal gas mileage. So the equality is always in the null hypothesis, along with the alternative that we don't want, which is that Americans get better gas mileage. Okay, so that we can reject that. Okay, so let me just check the questions there so far because that could get a little confusing, right? Okay, so now I'm going to do exactly the same thing I did before. I'm going to calculate my t-score. My t-score is going to be equal to, just like before, x bar minus mu, right, over the standard error. The standard error is the same thing that it was before. I don't remember what it was. You remember? Which was 1 point. Well, I'm not even going to bother doing that because I know that this comes out to negative 2.24, right? Because I haven't changed any of these numbers. Numbers are all the same, right? Negative 2.22. Now what I have to determine is this t that I calculated for this hypothesis, is this t greater than the critical value of t? So now what is the critical value of t that I need to exceed in order to reject this null hypothesis? Well, now I'm dealing with a one-sided test. In a one-sided test, remember before when we had alpha is equal to 0.05? 0.05 for a two-sided test, right? For a two-sided test, we put 2.5% at this end and 2.5% at this end. And for instance, if it were z, we had to have a z-score greater than 1.96 or a t-score bigger than 2.06, whatever it was, or on the other side also. Well, now since we're only going to do it single-sided, and since we're only looking at the probability of American cars getting uh, 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 worse gas mileage than foreign cars, I'm going to put all 5% down here. I don't have to put anything up here. So now I'm looking at the z-score here would be, well, if it had it been 5% on each end, I know that's the 90% confidence interval, right? So the z-score that would have been, the critical z-score that we would need is going to be equal to 1.64. But the t, I have to look the t up. Okay, so I'm going to go over and look the t up. Instead of 1.96, and we've been dealing with a large sample size. If they were at least 1.64 in a single-sided test, I could have rejected the null hypothesis, because anything bigger than that gives us a p-value less than 0.05 on that one side. Okay, so let's take a look at our t-table. Okay, t-table. Okay, here we go. So now, whoops, there it is. Yes, let's take a look at our t-table. T-table, single-sided 0.05. Right tail or left tail, doesn't matter, right tail or left tail probability of 0.05. That's the same as the t-score that you would use for a 90% confidence interval if you were calculating that, because then it would be 5% on either side. But for testing our t-value, well, we're only interested in one side, since we're only trying to see if what's the probability of it's being lower than that, okay, or greater than that for that matter. So 24 is going to be 1.71. Our critical value of t is going to be 1.71. And since we already know that it's 2.24, we know we've exceeded our critical value of t. So, but we really only needed to, we didn't need to exceed 1.96 to reject the null hypothesis the way we usually do for a single-sided hypothesis, a double-sided hypothesis. We only had to have enough distance between these to get a number of standard deviations apart of 1.7. A t-test is a less rigorous test. It's an easier test to reject your null hypothesis. So as a consequence, you really have to find justification for doing a one-sided test. You have to be able to say, there's no way, it's physically impossible for it to be the other way, to be greater, to be different on the high side rather than on the low side. So, I mean, there might be some instances where you can do that, but see, it's kind of, to use a one-sided test when you don't really have the background to do it, is kind of a cheat. It makes it easier to reject your null hypothesis. That's why we call it the less rigorous test, and that's why you almost always do two-sided tests instead of one-sided tests. Okay, so let's see. Okay, I'm gonna have to. Yeah, I'm gonna record this. It's recording. We only have like a short amount of time, so rather than going back through it again, this will be posted by tomorrow morning, so you'll be able to actually scrub back through it and take a look at this. So rather than like go back over this, I don't want to stop right now because I want to go on to the next couple of examples. But I understand that like it's a little confusing, but I think if you go back over it and work step through it again, the null hypothesis was rejected, right? Because our t value exceeded our critical value of t. It's a more standard, two values, the mean and the two means are more standard deviations away apart than we would need to have less than a 5% chance of being wrong. Okay, if you exceed your critical value of t or z, you can reject your null hypothesis. T was negative 2.2. The negative doesn't matter because negative is just a consequence of whether x bar or mu is bigger. And in this case, we know x bar had to be smaller because that's the assumption that we were going on in order to make it a one-sided hypothesis. They get lower. They get lower gas mileage. So if we, so it's only going to be negative. Had we had mu A is greater than or equal to mu F, well then X bar had to be bigger, otherwise we wouldn't even bother with this, right? If we were testing it on the other end and saying American cars had to be bigger, if the mean came out less, the mean of the sample came out less, and we were arguing that the mean of American cars is bigger than the mean of foreign cars, we wouldn't even bother because we know that even the sample came out less than foreign cars. So we don't need much more. There's no way we're going to prove that that it's greater than if even the mean of the sample came out on the wrong side. But again, usually you're doing two-sided tests. So I try and go through this again if we need to. We're going to be talking again about this. We're going to cover something called analysis of variance tomorrow, which is a way to calculate whether or not you have a significant difference between three means. T-test, and the t-test is determining whether or not you can say there's a significant difference between two means. For instance, group A and group B, male and female, and so on and so forth. Occasionally, you have situations where you want to compare more than two groups at the same time, group A, group B, group C, and group D, and you want to see if the means of any of those four groups are different from the other groups. So for that, use something called analysis of variance. It sounds like you're doing something else, but it is indeed, once you get a look at it, you get a feel for it. It is indeed something that you use to test the differences between means, even though we're calling it analysis of variance. Okay, and I think if you look at the first video that I posted for the lab, this thing about cherry trees and stuff like that, you'll see it. If you look at that video, I think it'll kind of give you an idea of how you can use variances to determine whether or not means are far enough apart to say that the mean of this group population is different than the mean of this population, and the mean of this other population, the mean of this other population, doing several at the same time without having to do multiple t-tests. But we'll talk about that tomorrow night. So let's get to one more part of this, at least anyway. That's a single sample t-test. So now paired sample t-tests are a special case. Paired sample t-tests, I'm going to open one up right now.